Hello, and welcome to the presentation of my dissertation. Before starting, I would like to thank you for reading and giving your feedbacks. Our research consists of 4 studies focusing on project forecasting using the Bayesian risk model. Before starting, I would like to present some brief concepts from the literature of project forecasting and Bayesian risk models. The dynamic scheduling model for effective project management consists of 3 phases: baseline scheduling, risk analysis, and project control. Each phase is supported with some measurable indicators, such as project indicators to measure the scheduling complexity of project instances, sensitivity metrics to measure the sensitivity of activities under risk and uncertainty. However, in real life, this process is actually not as smooth as this. It is often disrupted, which highlights the significance and necessity of project forecasting. However, as also expected, project forecasting is challenging due to the inherent uncertainty during project execution. In our dissertation, we refer to the measurable drivers of this uncertainty as project risks. In traditional forecasting methods, these project risks are assumed to arise independently from each other. However, in risk models, we consider and we acknowledge the causal interaction between these project risks, meaning that we focus on their holistic impact on the final project performance. However, this risk models is not new to the literature. They have been applied before, but with quite a few limitations. The previous research relied on qualitative and contextual project risks, which reduce the generalizability of their models. They structured their risk models based on expert knowledge or expert assumptions. And finally, they are usually validating their methodologies with limited amount of case studies. However, in our research, we propose a methodology to generate a fully data-driven risk model using quantitative metrics from the dynamic scheduling literature, and we validate the results of our methodology or the results of our risk model on a wide variety of project data, both artificial and empirical. Each research study is presented in a separate chapter using a different version of their Bayesian risk model. In the remainder of this presentation, I will present them in detail. In this chapter, we propose our initial risk model, which is the foundation of the following studies. We have 2 main objectives. The first is to generate a fully data-driven risk model. To that purpose, we use 2 different methodologies. First, we propose and validate a theoretical model using the structural equation modeling. And then we train the model and then utilize it for forecasting using the Bayesian networks. Once the model is trained and tested, we benchmark its accuracy output against selected traditional forecasting methods. This table summarizes the characteristics of the risk model of this chapter. It is static, meaning that it is forecast, meaning that the model is utilized one time before the project starts. And the model operates at the project level, meaning that it directly forecasts the final project performance. The model only considers precedence constraints using network indicators and time and cost sensitivity metrics. This is the theoretical risk model that we propose for this chapter. We propose using time sensitivity and cost sensitivity of projects as risk variables, in addition to the network topological characteristics. This theoretical model is then validated using 9 different artificial data sets with varying levels of duration and cost uncertainty. The validation resulted in 2 different model structures. One retains the cost sensitivity, while the other excludes. This difference is shaped by the level of cost uncertainty in the different training and validation projects. Both of these models are then used for forecasting the final duration and cost performance of 33 empirical projects. The results indicate that the risk model is more accurate when variability in the training data is more or less similar with the one in the test data. As you can see from the box plots, on the x-axis, we see the increasing distance between the variability in the training data and test data. As it increases, the forecasting error also increases. When we compare the accuracy of the risk model against some static benchmarks, we observe that the risk model performs more accurate time forecasting and cost forecasting on average, with only one exception, which is when the deviation from the baseline schedule is extremely high, we observe that the machine learning algorithms perform more accurately than the risk model. When we compare the accuracy of the risk model against dynamic methods, we see that the risk model is more accurate in early stages. However, when the project enters to its second half after the 50% completion, this advantage disappears and the dynamic methods start outperforming the risk model. In the following chapter, we extend the risk model of chapter 2 with resource-related risk variables. Our first objective is to integrate them optimally through a stepwise approach. Our second objective is to investigate the impact of scheduling flexibility and duration uncertainty of test projects. To that purpose, we consider various settings having re-optimization or different execution policies in test projects during simulation. Finally, we again benchmarked the accuracy of the results against traditional methods. This table clearly highlights the difference of the risk model in this chapter when compared against the previous one. We additionally consider resource constraints, and we also integrate the resource indicators and resource sensitivity metrics as risk variables. This is the theoretical model that we propose for this chapter. We use the network properties, time sensitivity, and cost sensitivity from the first chapter, from the previous chapter. Additionally, we consider the resource sensitivity, resource-considered time sensitivity metrics, network resource properties, and pure resource properties. Some of the observable indicators to measure these risk variables are traditional. Some are recently proposed by other researchers. As you can see from that theoretical model, now we have a large number of risk variables, so we need to be sure that we only consider the significant ones. For this, we propose a core model consisting of network properties and resource time sensitivity, and we add the remaining variables one by one to the model, and we measure its contribution on the overall model fit. So these risk variables are either retained or excluded from the model, depending on their contribution to the overall model fit. Once we obtain the model, we use it for forecasting the time performance of unseen artificial projects. Further, we validate our results using empirical projects too. The first result indicates that the newly integrated resource-related risk variables improve the accuracy. This is important because it also validates that the recently proposed resource-related sensitivity and indicators, indicators are valid to be used for project forecasting in addition to their original purposes, like scheduling or risk analysis. Secondly, the results show that the risk model is truly sensitive to the accurate estimation of flexibility in the training data, flexibility in the test data. So therefore, we can observe that the risk model is more accurate when the flexibility in the training data and test data are more or less similar. And when this condition is satisfied, we observe that the risk model is more accurate than the benchmark methods, even under increasing uncertainty as observed in x-axis of the graphs. Finally, we see from the results that the risk model performs better than the benchmark methods in parallel projects. And this is logical that in such projects, the risk variables that we consider, sensitivity metrics, network indicators, or resource indicators, are higher in variation, so which means that they are more meaningful to be used. In Chapter 4, we utilize the risk model of Chapter 3, dynamic, which means that we update the forecast as the project progresses. To that purpose, we recalculate the project indicators and we resimulate the sensitivity metrics based on the removal of finished activities at each tracking period. Further, we also investigate the impact of updating risk variables selectively and also the impact of percentage completion of the tracking period on the forecasting accuracy. To that purpose, again, we apply lots of different training and test strategies. Finally, similarly, we compare our accuracy with some selected dynamic benchmark methods. This is a clear indication that the risk model of this chapter is only different than the risk model of the previous chapter in terms of its dynamic application. In this chapter, we use two different training strategies. First is the contemporaneous strategy, where it maintains the existing risk model structure of the previous chapter and use it at different tracking periods, meaning that this strategy do not consider the actual progress data. However, the integrated strategy builds on the existing risk model and adds two new risk variables. It's PT and PC, reflecting the time progress and cost progress at different tracking periods. Both trained risk models are then used for forecasting the duration performance of artificial projects. Similarly, they are also validated using empirical projects too. The first result indicates that the dynamic risk model consistently outperforms the static risk model. One indication is that only when, for serial projects, in the second half, the advantage of the dynamic risk model starts decreasing, as in such projects, serial projects nearing completion, the variation and the meaning of risk variables again start to disappear. Our second result indicates that the selection of the most accurate training strategy must depend on the network topology and percentage completion, as either one of the training strategy is more accurate depending on the topology and the percentage completion. Similarly, we try to answer the question that says, do we need to update all risk variables at each tracking period? It's computationally loaded. So we want to reduce that computational load. So for that purpose, we tested 16 different combinations of the risk variables to be updated at each tracking period. So we obtained such a heat map indicating that selectively updating the risk variables yields better results than updating all variables at each time. It must be selected again based on the network topology measured by the SP and the percentage completion of the tracking period. Finally, when we compared the accuracy of the dynamic risk model against the benchmarks, we observed that the best method varies for the network properties, resource scarcity, and the percentage completion. But in summary, we can say that the dynamic risk model works better for parallel projects under high resource scarcity. In the last research study, we changed our perspective from project-level risk model to the activity-level risk model, meaning that our ultimate objective is to consider the activity-level variability during project forecasting. For this, we use activity indicators instead of the project indicators that we use in previous chapters. This is achieved in three different risk model frameworks. First, in Model P, we aggregate the variation in these activity indicators at the project level and aim at directly forecasting the project duration again. In Model A, we apply the forecasting and the risk model directly at the activity level, meaning that we forecast first the activity durations, then we convert them into the project duration. Similarly, in Model C, we forecast the activity durations, but we only forecast them selectively. For when utilizing Model A and Model C, the project is scheduled one more time using the forecasted activity durations in order to obtain a final prediction for the total project duration. All of these three models are then compared against the original risk model framework of the previous chapters where we used the project indicators. So this summary shows us that in this chapter, we operate the risk models both at project level and activity level, and we investigate the impact of forecasting the activity performance first and then obtaining the project performance. To that purpose, we propose two new theoretical models. First is for Model P, where we propose two risk variables, resource properties and network properties. For resource properties, you see that all three indicators are accepted: total resource demand, total resource scarcity, and resource work content. For network properties, we propose 6 different indicators, but only most successors per level, immediate successors, and positional weight are found to be significant to be used. Taking lead from this information, we train activity level risk models. We only use the validated observable indicators and assume that they are directly affecting the performance of the activities. Here, it's important to note that the positional weight and immediate successors are the ones that has more significant impact on the final activity duration. Please keep that in mind. Our first results indicate that, on average, Model P and Model R are only marginally different in terms of the accuracy, which means that when we use activity indicators, aggregating them at the project level have little to no impact. However, as we can see from here, the Model A performs significantly better than the other two methods for at least 60% of projects. Additionally, we observe that for the remaining part of the projects where the other methods perform better than Model A, we observe that still Model A doesn't have some spikes in the errors or extreme problematic accuracies. It's also the one with more robust forecasts. So we can say that Model A performs better than Model R, the original approach, and Model P, which aggregates the indicators at the project level. Secondly, I told you that please keep in mind that we have the most significant indicators as immediate successors and positional weight. Using these two indicators, we cluster the test projects through a clustering algorithm. And we applied forecasting through the Model C by only forecasting the activities in each cluster separately. And we resulted that selecting activities based on cluster 1 is better than a random selection where we randomly select 60% of activities and forecast them. So we can say that the clustering approach based on immediate successors and positional weight makes sense. Please try forecasting activities with low immediate successors on average and low positional weight on average. And when we compare the accuracy of Model C when we only forecast the activities in cluster 1, we can say that for some projects, Model A performs better, where we forecast all activities. For some projects, Model C is better. In summary, we can say that model C is better when the duration uncertainty is low to moderate, meaning that under high uncertainty, it is better to forecast all activities. And in parallel projects for parallel networks, model C is better than model A. Other than that, for serial projects, we should rely on model A. So this chapter, in just 2 slides, I will summarize the results of our written research studies and some future implications. In summary, very briefly, we proposed to use risk models, relying on quantitative project metrics as forecasting the final duration performance of projects. In chapter 2, we learned that our risk model approach is a competitive alternative for project forecasting when compared against the traditional methods. In chapter 3, we observed that integrating resource-related risk variables, which are the newly proposed sensitivity metrics and complexity indicators, improve the accuracy of the risk model. In chapter 4, we observed that we can use this resource-integrated risk model dynamically, and it's also a competitive alternative to the well-known earned-value management, especially for projects having parallel structures and high resource scarcity. In the last chapter, we tested the activity level risk model approach, where we focus on the quantitative indicators to measure the significance of activities rather than the project. And we observed that it results in more accurate forecasts when compared against the project level approach. So our future research aims at using the risk model, the lessons learned from the risk model approach for designing proactive corrective actions. And I plan to use them in 2 separate phases, where the project level risk model will be used for performance monitoring even before some problems occur. And then as a second phase, maybe we can use that activity level risk models to select the corrective actions and to see the impact of these actions on the forecasted activity duration. Thank you for listening to the presentation. I think I'm finished now, and I hope to see you on the public defense. Thank you in advance. Have a nice day.